Welcome to our lesson video on training and assessing model accuracy. The first thing I want to talk about today is how to assess the accuracy of a model. This process is called validation. So here in our plot on the left-hand side of our screen, we have a regression model that we're trying to do, and we're trying to predict income as a function of years of education. And so I can put in a model, which I'm representing with this blue curve that's approximating the function for income as a function of years of education. And so I want to know, how accurate is this model? The formula we use, and this is something you're likely familiar with, is called mean squared error. And so the formula is on the right-hand side there. And here's how we understand this formula. We look at each data point, and this vertical black line for each data point shows us the distance between that data point, which is y subscript I, or the actual value of the output for xi, and the curve, which is f hat at xi. And so that represents our error, which is given in this part of the formula. And so the mean squared error, we just take the square of all those errors and then take the mean. And that's the standard way to measure accuracy for a regression model. Now for a classification model, the formula is going to be a little different. And on the left-hand side here, I have some classification data. So this is a standard data set, one we're going to see a couple of times in this course, and this is called Fisher's iris data. And so a biologist who became, we call him a statistician, but he's really the father of statistics, father of modern statistics, Ronald Fisher, in the early 1900s, 1930s or so, measured a number of flowers. They were irises, and he measured four different parts of the flower. And so what we have here are two different of those measurements, the sepal height and the sepal width, and this scatter plot. He measured this for three different species of flowers: Virginica, Verticolor, and Setosa. And so what we have is a scatter plot here of the sepal width and sepal height. The Setosa flowers are represented in red, Verticolor in blue, and Virginica in green. And so what we do to look at how accurate our classification model is, our model here is represented by a red region, which is what the model declares anything in that red region as being the red category, or Setosa. There's a blue region, and anything in that blue region is going to be labeled as Vertica. And there's a green region, and any values that are going to be in the green region are going to be labeled Virginica. And so we see a couple of errors here. So right here are data points that are actually Verticolor, but they're in the Virginica area, in the green area, and so we're representing those with an X because they are incorrect. And right here I've circled in gold a couple of green X's, so those are actually Virginica colors, but they're not in the Virginica area, so they're incorrect. And here's one, Setosa, that's incorrect. And so when we're looking at classification, we want to know, how accurate is my classification model? We just look at what's called the error rate. It's the number of data points that are incorrect divided by the number of total data points. This is the error rate, the percentage of data points that have been labeled incorrectly. It is sometimes written the way we have in this formula shown here. And in this formula, N is the number of total data points. And in the formula, this function I is an indicator function. So that function capital I is going to be 0 if the thing inside of it is false, and 1 if the thing inside of it's true. And so when we sum up over all our data points I of this formula, that just gives us the number of incorrectly labeled data points. Another measurement we might want to talk about is percent accuracy. This is the number correct over the number of data points. Of course, percent accuracy and error rate measure the same thing. Percent accuracy is just 1 minus the error rate. Just two different ways to look at the same thing. And it depends on the user whether they would care about percent accuracy or error rate. Statisticians tend to like error rates. Percent accuracy The user may want to see more often, oh, this is 96% accurate. It gives them some sense of feeling that may be more meaningful intuitively than saying there's a 4% error rate. Now, when we're doing validation, we're testing our algorithm. We actually don't want to test it on the same data that's been used to build that algorithm or to train that algorithm. So what we do is we create what's called testing and training data, or testing and train data. And so what we do is we take our data set, which is represented over here on the left-hand side. This is mimicking a data set with a number of rows, and supposing there's two different classes, which we're calling blue and orange. And we pull out some random sample of that data, and that's going to be our training data. So we're going to label, use to train our model. And suppose we take that data and we plot it here, and I'm going to pretend to be model. And so I'm going to suppose that's representing my model. So everything on this side is going to be labeled orange. And everything on the other side of that curve that I drew is going to get labeled blue. So my green curve here is my separation curve. Everything on one side is going to be labeled orange, and everything on the other side is going to be labeled blue. Of course, since I can draw that curve to separate the two classes any way I want, I can draw it to get perfect accuracy on my training data. But now I pull out my test data, which was all my data points other than my training data, and I find, uh-oh, I've got a data point here that was outside of my my boundary for its class. And so what's happened here is this loop that I drew, it trained around what appears to be a nuance that was in my training data that's not present in my test data, so I'm getting an error on my test data. And so the point in this demonstration or this visualization is that you don't want to test your data on your training data. You want to test it on the testing data. So testing and training data principles, we always evaluate performance on the test data. Sometimes we have an additional what's called holdout data set, and we evaluate our different algorithms and we optimize and set the parameters, something we'll talk about, on our training and testing data, and then we have a separate data set that we don't look at until later, and that's what we do our final testing on. And just typically, when we split our data set into training data and testing data, we usually use roughly 75% of the data for training and 25% for testing. That's not a hard and fast rule. Sometimes you'll see 2/3, 1/3, 80/20. Depending on the data set and what people are doing, they may do a 50-50 split. Depends also on how much data they have. But typical rule of thumb is 75-25%. Now let's talk about something called the bias variance trade-off. We've talked about this a little bit before, and so we're going to talk a little bit in more detail. So here we have figure 2.9 in our textbook. And on the left-hand side, we have a regression problem. The open circles represent our data points, and then we have three different regression methods that are giving three different models, one shown in gold, one shown in blue, one shown in green. And the goal here is predict the output values y as a function of the input values x. That's the left-hand side. On the right-hand side, we have a plot of what's called the flexibility of the model on the x-axis. Flexibility here refers to how much the model is allowed to wiggle, how far it can get away from linear function. And so we're going to talk later in later chapters about how those types of more flexible models are built for regression. But for now, just understand that this x-axis is a measure of flexibility. And on the y-axis on this plot on the right-hand side, we have the mean squared error. So mean squared error, better is of course lower values. So we want closer to zero error. Okay, now on the left-hand plot, we have three different methods for regression. So let's go through and see how each of these methods are doing. So the first method is this gold method, and this is a straight linear regression. And the mean squared error for the gold method are represented here on the right-hand plot. And on the right-hand plot, we have two values giving us errors. So what's shown in gray is the error rate or the mean squared error on your training data, and what's shown in red is the mean squared error for your test data. And so you'll notice for our gold regression, our linear regression, we see that both the training error and test error are high. The gold regression wasn't even able to get a good error rate on our training data. Then the next model we might want to look at is shown in blue. And here. And we can see the test error right here for that model is low, and it's almost equal to the training data error. They're not far apart. And so that's a good indication. Out of our three models that we're looking at, the gold and the blue and the green, this blue is the one with the lowest test error. So out of these three, we should say that this is the best model. This is the one that's giving us the best performance. The third model here is shown in green. And here's the test error rate and training data error rate for the green model. And what we have is the green model has a high test error. It's so flexible, it does very well on our training data, but the test error is too high. And so this green model has what we call, we've talked about this in the previous videos. The green model here is what we call high variance, or a tendency for high variance errors, or to get errors because of its variance. The gold model, write this over here, has high bias, meaning there's a bias that's built into this model that doesn't match the data. And when we say the model has high bias, mean it has a tendency to get bias errors. And so what I want to talk about now is a little more rigorous view of the variance error and the bias error. One more terminology that we're going to see a lot that we should talk about. This gap, when this gap is large between your test error and your training error, we're going to see this a lot. This is called overtraining. Right? So when your model has trained very accurately on your test data, but has trained very accurately on your training data, but that accuracy is not represented when you look at your test data, that's called overtraining. And when we look at our green model over here on the left-hand side, if you look at the green, it's doing a lot of squiggling up and down and jumping around to try to match these small wiggles that are present in our training data on the left-hand side, but it wouldn't be present in our test data. So we have a similar set of plots here, and I'm just going to walk through these very quickly. When we look at these plots, this is similar plots. The only difference here is a different data set. Now our linear model shown in gold has a very small separation between the training error and the test error. Maybe the light blue has a little lower test error right here. So the gold or the blue would be okay in this case. The green would not be okay. Again, we're seeing out here evidence of overtraining, and if we look at the green here, the way it wiggles around and adjusts to every fluctuation in our data, that's evidence of overtraining. Okay, let's look at the bias variance trade-off a little bit more rigorously. And so here we have y equals f of x plus epsilon. So that's our standard way to say y value that goes with x is equal to some function of x plus some error. And when we look at on the left-hand side, it's the expected value of the difference between y and the predicted value, right here. This is an expected value for error squared. And on the right-hand side, let's take these terms one at a time. This, switch colors. This piece right here, it's the prediction for our model minus the expected value for the prediction, and then squared, the expected value of that difference squared. And so that is a formula for variance. Now, this big formula that we're working with here, you can start with the left-hand side and walk through a fair amount of algebra and then get to the right-hand side. We're kind of skipping this step and taking this formula as a given, which follows what our book does. We don't need to get into, take the time to go through the full derivation of this. We're just going to use this conceptually over and over through the course. So it's nice to see where this idea of variance and bias comes from. This piece inside the brackets here, it's the expected value of the output of our function minus the actual value for y. And so this is what's called a bias. So what we get is the left-hand side is the error that we see from our model, and we can decompose that into the variance shown in the red here, the variance error, and then the gold is what we have as bias error, and that's squared. And then this last piece here, this variance in epsilon, remember epsilon is this difference between the actual function f and the output of y, and this is what's called irreducible error. And so that's what the goal in data mining is, to find a model that will have low variance error and low bias error, but we can never decrease below the irreducible error. We can never decrease the irreducible error. Way to visualize this, and this is kind of a standard way to visualize it. Previous slide was the technical formulas. We have 4 targets here. The 2 columns, get a pen. The columns correspond to the left-hand column is low variance, right-hand column is high variance. And so the variance, remember, it tells you how spread out your data. So if you look at the hits on our target on the left-hand side, they're all tightly grouped. That corresponds to a low variance, and on the right-hand side, they're more spread out. That corresponds to high variance. The top row corresponds to low bias. So the average of our hits on our target is close to the center in both of those on the top. On the bottom, we have high bias. So the average from a prediction from our model is off target by some preset amount. And so that's what we talk about when we talk about bias. So the bias is how far we're off, which is shown by these arrows in the bottom, and the variance we think about is how spread out our output from our model would be. Review of our things we've discussed in this video. First, we talked about validation. We talked about mean squared error and error rate. Those are our ways for measuring validation for regression classification. Then we talked about training and test data and the importance of checking your validation on your test data, not your training data. And then we talked about the bias variance trade-off. Bias variance trade-off is something that's going to come up a lot in this course. We talked about it rigorously in this section, although we'll often talk about it more conceptually in helping us understand different models. Thank you very much.